you to my lecture today. Of course, today I'm actually going to be walking you through another exciting topic in statistics. Uh, I need you to confirm if everyone is hearing me clearly. Is everyone hearing me clearly?
Yeah.
Okay, thank you so much. Once again, I want to welcome you to another statistical party. Of course, I'm actually going to say this is a party, okay? And I hope at the end of the day, you're basically going to enjoy every of statistical concept that I'm actually going to be passing across. Okay, before I get started today, I actually want to say that our previous recordings have already been published. I will advise that you check, the course module to have access to that. Okay, give me 1 second. I'm actually going to share my screen right now. Okay, so the material that we actually, the material we started on Monday, we finished that material on Tuesday. And of course, the material that we want to work on today is basically the material for Tuesday. Okay, so as you can see, June 7th. So the title is Probability on Finite Sample Spaces, Part 2. Okay, it means we are still on probability of finite sample spaces. And you know what, the outline today, we actually going to talk about finite probability models. From there, walk you through statistical models. Some of you may be wondering, like, is there any difference between statistical models and probability models? Okay, I'm actually going to walk you through them today. Then from there, we talk about random variable and expectations. Okay, so let's get started. Okay, so let me first revise with you. The other time you were introduced to probability models. I told you we find ourselves in a world that is stochastic in nature. Okay, we live in a probability space, and you know what? If we want to take a decision that we don't want to regret, maybe we want to take economic decision, we want to take political decision, or we actually want to take medical decisions. And probably we want to understand, before we can actually do that, we need to understand our environment. And you know what, the environment we find ourselves in, like I said, is probabilistic in nature. And that is the reason why we need to be able to understand some basic probability models, for us to be able to figure that out. Now, I want to put it to you now. When we say probability models, what do we mean? The probability model is actually the mathematical representation of, a natural phenomenon. Okay, the mathematical representation of that. So, previously I told you we basically using model to capture reality. And you know what, because reality is probabilistic in nature, and therefore we basically need to use a probability model to capture probabilistic reality. Okay, so that is it, because there must be a kind of an agreement between the model and reality. And since reality is probabilistic, then we got no choice. We're actually going to use a probabilistic model. And you know what? We got two types of probability models. We have a finite probability model, and we have an infinite probability model. And you know what? Well, what I'm just going to be walking you through in this course mostly will be finite probability models. What do I mean by finite probability models? Okay, what I mean by finite probability models is actually, every probability model have a sample space, right? Okay, now, and don't forget that I actually told you the other time, the sample space actually means collection of possible outcome in an experiment. You remember on Monday, I said we find ourselves in a world where we experiment. It is not until you are in a physics lab or you are in a biological lab before you can experiment. The life itself is an experiment. Whatever you do that generates an outcome is an experiment. So the probability model that we talk about, every probability model have a sample space. And you know what? When a sample space, if there's a limit to the numbers of elements that we have in the sample space, then we call that probability model a finite probability model. I'm going to say that again. But it is exactly what I'm trying to say. The probability model is divided into finite probability model and the infinite probability model. And you know what happened now? We are talking about the finite probability model. We're basically talking about the sample space, whether if the sample space, if the element in the sample space can be counted. Okay, if you have a countable numbers of elements in the sample space, then such probability model is a finite one. Okay, but if there's no limit, okay, I'm going to give you an example of a sample space that have a finite, that is finite. Okay, take a look at this guy now. I have a 1, 2, 3, 4, 5, 6. That's a finite because there's a limit to the numbers of elements it contains. Okay, I'm going to give you an example of infinite right now. Okay, if I have 1, 2, 3, and I continue, take a look at that. Okay, that's an infinite. Okay, but you know what? The one we're going to be talking about, okay, is actually going to be finite. Okay, so that is what I mean by that. Okay, now, when you are talking about finite probability model, a model, okay, if you're talking about finite probability model, okay, so what we actually want to say is this, okay, at least we're basically going to have some elements, okay, so if we want to start, the most simplest form of a sample space is when there is one element. Okay, take a look at this. Okay, you have a single element. The element now is S. Therefore, the probability associated with that particular element is actually going to be equal to 1. Okay, and let me tell you this. Situation where there's only one element in a sample space, we call that, a sure event. The probability, that would be a sure event. A sure event in the sense that, of course, that event is always going to happen because it's like you're having one state of nature. Well, but let me tell you this. Under the sun, there is nothing like this. This is not realistic. It is not possible for us to have just one element in a sample space. I'm just, we're using this for, for just explanatory sake. That was why we said here, if you take a look at this statement, I said, this probability model is of no interest in applications. Don't forget, I told you the other time, we live in a stochastic world. What make the world stochastic is because of variations. Okay, we expect to have more than one event in a sample space. We are not going to have just a single event. Okay, but I'm using this as explanation now. You get what I mean? Okay, this is of no interest in application at all. But you know what? Just for explanation's sake, Okay, and we're basically going to refer to this as, the simplest form of all probability models. And you know what I'm talking about right now, actually focusing on, finite probability model. Okay, now that is one example. I'm going to go to another example now. Now, when you take a look at this example, is what of in a situation where we got two spare, element. Look at that. This is reasonable. Okay, when you have two elements in a sample space, that's reasonable. I'm going to give you an example of this now. It's either a particular team win a championship or not. Okay, X1 maybe is an event of winning a championship, and S2 is an event of not winning a championship. Okay, I can also refer to that as probably when I have a fair coin. Okay, we got two sides in a coin, right? Head and tail. Okay, so that's an example of a sample space with two elements. Okay, and you know what? I actually told you the other time that uh, you know every element in a sample space has its own probability. Take a look at this now. If I have an x1, the probability is going to be f of x1, which is equal to p. Oh, if that x1 represent event of a team winning a championship, then f of x1 equal to p is basically going to be the probability of winning a championship. Okay, if x2 is the probability of not winning a championship, then f of x2 is basically going to be equal to 1 minus p. Why is it 1 minus p? Don't forget, we expect f of x1 plus f of x2 to be equal to 1. You remember yesterday, one of the property of probability mass function, the sum of the probability, the sum of the function must equal to 1. You get what I mean? Okay. Now, if don't forget I said f of x1 equal to p. So p plus f of x2 equal to 1. So if I want to get the f of x2 now, it's basically going to be 1 minus p. So if I now want to define a probability mass function for the process, then I'm actually going to have this guy here. Look at that. Okay, the PMF, that we call the probability mass function now, the probability mass function for, for sample space that have two event or two elements, okay, there is actually going to be written like this. We're actually going to have the f of s equal to p when s equal to x1, and f of s equal to 1 minus p when s equal to s. True. That is what it means. Okay, and you know what? Is there anyone who need clarification on what I just explained right now before I move to the next slide? Is there anyone?
So fx1 means the probability of occur for the x1 event, right?
Can you say that again?
Fx1 means the probability of occurring the x1 event, right?
Exactly. The f of x1 actually means the probability of the occurrence of x1. That's what it means. So which is basically p. You are right. Okay. I wanted to actually relate. I just use a championship right now, a team winning a championship or not. Okay. Another example could be attending my lecture right now, or you don't attend my lecture. In your sample space, the X1 may be the event of attending my lecture. And X2 would basically be the event of not attending my lecture. And I told you the other time, every event in a sample space has a corresponding probability. Okay. Now, I want to move to the next. When you are talking about two events, situation where you have, two events in a sample space. We have a brand name. We have a name. We have a statistical distribution. Name for that. We call that Bernoulli. distribution. Let me tell you what Bernoulli distribution actually represents. Bernoulli distribution in statistics actually captured dichotomous outcome. You know, when I say dichotomous outcome, what do I mean? You know, uh, when in an experiment, when you have two possible outcome, if there are two possible outcome, if you take a look at the one I define here, it's basically X1 and X2. You get what I mean? You only have two possible outcome. So the name of that distribution in statistics is what we call Bernoulli distribution. And you know what? I give an example here. Take a look at that. Okay, if the actual space of interest is I have in my sample space, maybe I got apple, I got orange, you get what I mean? And you know what? That we actually map this to Bernoulli distribution. Why are we doing that? Because Bernoulli distribution actually model two possible outcome. Experiment that have two possible outcome. And you know what? We can actually introduce a random variable here. Okay, we can actually say, okay, let's code apple as 0 and let's code orange as 1. Why am I doing that? I'm doing that because, I told you the other time, a random variable is a way of assigning figures to elements in the sample space. Okay, where 0 is going to represent apple, 1 is going to represent orange. Okay, now if I now want to define my random variable x now, okay, it's basically the range of that is going to be 0 and 1. Okay, that's exactly what I mean. And you know what? That distribution is Bernoulli. But you know what? We're still going to talk about some statistical probability distribution. Okay, now from there, I want to move to statistical models. Let me tell you this. Statistical model is a family of probability models. In statistics, we have different kind of probability distribution that can be used that we call Bernoulli, binomial, geometric, hypergeometric, negative binomial, normal distribution, gamma distribution, exponential. There are so many probability distributions in statistics that actually model different kind of real life scenarios that I'm actually going to walk you through. But you know what? One of them is Bernoulli distribution that we talk about. Okay, now Bernoulli distribution is this is a definition. Mathematically speaking, the probability mass function of a Bernoulli distribution. We normally the notation that we use is this: B E P. What is P? P is a parameter. You remember every distribution has parameter. Okay, the parameter of a Bernoulli distribution is P. And what is P? So P is basically going to be the probability of success, because in a Bernoulli distribution where we have two outcomes, it's either we have a success or we have a failure. If we have a success, what is the probability of success? The probability of success is actually P. Okay, and the random variable for that is S equal to 1. What is the probability? So this is like events, okay, events of success. Okay, this is events, okay, of failure, okay, and this is the probability of success, okay, P, the probability of success, and this guy here, probability of failure, okay, probability of failure. Take a look at that. Okay, I told you, anytime you have an event, you have a corresponding probability for that event. I wanted to picture this as if you're doing business. When you're doing business, it's either you make a profit or you make a loss. I can refer to event of profit as event of success. I can refer to event of loss as event of failure. And what is the probability of making profits, I'm actually going to refer to that as the probability of making profits, which is P right here. And what is the probability of making loss? Then I can refer to that as the probability of failure, which is 1 minus P. Take a look at that. It means Bernoulli distribution can actually be used to model a dichotomous outcome. You know, outcome that have two possible nature, either success or failure. That's exactly what we mean here. Okay. And you know what? If I want to write the PMF, I'm actually of Bernoulli distribution, I'm actually going to say f of x equal p raised to power x, then 1 minus p raised to power 1 minus x. And you know what? S start from 0 to 1. Look at that. This is a PMF. Okay, that is a mathematical expression for Bernoulli distribution. There's something I want you to do now. Okay, plug in 0. Okay, when you plug in 0, what do you have? When you plug in 0, automatically, you're only going to have 1 minus p, which is this guy here. Look at that. You can plug in 0 here, you know, f of 0 is going to be what? P raised to the power 0. 1 minus p raised to the power 1 minus 0. What do you have? This is 1. Then automatically we give you 1 minus p, which is this guy here. When you plug in 1, okay, when you plug in 1, okay, it's basically going to give you p. Okay, just wanted to take note of that. Okay, so that is for Bernoulli distribution. And of course, P lies between 0 and 1. And when I say P lies between 0 and 1, it's actually going to be close at both ends. You know, this guy means 0, 1. You understand? The other time that I introduced you to different kind of intervals, you know, we did that yesterday. Okay, the interval for P now for Bernoulli distribution is actually between 0 and 1 inclusive. Okay, can you say confirm if you're still hearing me clearly? Is everybody still hearing me clearly? Okay,
Yeah.
thank you so much. Thank you for confirming that. Okay, so Bernoulli distribution is a family of probability distribution. I just wanted to know that. Now, I want to go to the next example now. In the first example, don't forget we're still talking about finite sample space. You know, we're working with a finite probability model. And you know what? Working with a finite probability model, you know, we're actually trying to say the is a limit to the number of elements that we have in a sample space. You know, I've walked you through an example where you only have one event in a sample space that I said is not realistic in this world. And I also walk you through an example, you know, of a finite sample space where you have two events. And right now, and I want to talk about where you have three events, X1, X2, X3, okay? Because at time we could have more than two events in the sample space, okay? What of, you know, I use an example of a team the other time, winning a championship, okay? If I want to talk about a game of a soccer, where a team play a game and you know, a game can, you said that the team win a game or you lose a game or you draw. There's possibility, you know that, right? Three things could happen when you play a game. Like I'm talking about soccer game now. Okay, you said that you win, a team win a game, win a match, or lose a match, or draw a match. That's an example of, you know, a sample space having three events. You get what I mean that I'm talking about now. And each of them will basically have their corresponding probability. Take a look at this guy now. You know, when X1 is an event within a sample space, the probability is basically going to be f of X1, which is equal to P1. And what about for X2? You're going to have that. What about for X3? I'm going to tell you this. F of X3 is also P3, but only that we don't want to talk about P3, but this is what we want to do. You know that F of X1 plus F of X2 plus F of S3 equal to 1. So if I basically want to find F of S3, what I'm going to do, okay, is just going to be 1 minus f of x1 minus f of s2. And you know what? And I'm going to say 1. What is f of s1 p1? What is f of s2 p2? That's exactly what you have here. Take a look at that. Okay, take a look at that. Therefore, what is the PMF? This is a PMF now for different values of X. You're actually going to have different probability. The probability of winning a match is different from the probability of losing a match. It's different from the probability of a match ending in a draw. If I really want to know that, of course, we're going to look at the number of matches played, by a particular team in the past. How many of them? Okay, I'm going to give an example right now. You know, uh, last week there was a Champions League final, European Champions League final between the Real Madrid of Spain and Liverpool of England. And of course, there was a lot of predictions before the match. I think in 2018, the team actually met in the final, and the Real Madrid actually won the match 3-1, but they met again in 2022 European Champions League final. And maybe before the final game, statistician may actually, or sport analysts may want to determine the probability of the game ending in winning for Real Madrid, winning for Liverpool, or draw. Okay, so what I'm trying to tell you now, the probability, when you have different kind of event, then they're actually going to have different probability. Exactly what I have right here. Okay, now, because of that, in that situation, we basically, when you take a look at this, where we are actually silent, we silent on P3, because when you take a look at this guy now, it's more or less like a P3, but we are silencing on that, because 1 minus P1 minus P2 is basically going to represent P3. Because of that, we're only going to say, if you take a look at what I have here, it's just a functions of P1 and P2. So because of that, we're basically going to write this. Okay, that is why we are writing this right now. Take a look at that. Oh my God. And that was why I say, instead of saying we have two parameter P1 and P2, we can say we have a two-dimensional parameter. Okay, the vector P equal to P1, P2. Take a look at that. And don't forget, when you have a two-dimensional when you have a two-dimensional parameter like that, then you basically, if you want to talk about real number, then it's going to be real number squared. Okay, because you have a P1, actually from real number, there's another P2 also from real number. So if I want to write it in a vector form where I'm going to combine the two, the P1 and P2 will basically come from real number squared. That's exactly what we mean, and that's what we're talking about here. And you know what? We actually want to impose a condition on probability. The P1, the probability has to be non-negative. The P1 and P2 has to be, so that it is 0 or greater than 0. We can never have a situation, where the P1 or the P2 is going to be negative. Okay, it's actually either going to be 0 or more than 0. And you know what? We have another condition, that the addition of the P1 and P2 in a two-dimensional parameter vector has to be less or equal to 1. Okay, I just wanted to take note of that. It has to be less or equal to 1. Okay, and the only condition on that is P1 plus P2 can actually be equal to 1, then you are actually saying the P3 equal to 0. Okay, that's exactly what you mean. Okay, so take note of that. Now, I need to confirm again if everyone is still hearing me clearly.
Yeah.
Okay, is there anyone who want to ask question at this time before I move on? Is there anyone who need clarification?
I had a question.
Okay, go ahead.
So do all probability distributions with a sample space of 3 elements have a two-dimensional parameter vector?
That's a very good question. Yes. You know why? Because we can, on a normal ground, they should have like 3, like P1, P2, P3. But because, take a look at this guy here. Because P1 plus P2 plus P3 must be equal to 1. So therefore, I can express P3 as a function of P1 and P2. Does that make sense to you now?
Yes, that does. Thank you.
You're welcome. So that is the reason. because we can express P3 in terms of P1 and P2 using the fact that the sum of a probability has must be equal to 1. That's a very nice question. Oh my
So
God.
if it's
Okay.
four events, we can have the 3-dimension, right?
Exactly.
Okay.
Because in that situation, you have the P1, P2, P3, P4. Okay. And in that case, P4 in that case will be 1 minus P1 minus P2 minus P3. That is it. You are right. Very correct. Okay. Now we're going to keep going now. Okay. Now, we visited the other time we talked about statistical model, and I said statistical model is a family. Give me 1 second. Let me check my chat. Okay. I thought, you can ask me question. You can also chat with me if you don't want to talk. Okay. So, but feel free. Okay. Feel free to ask me question. Okay. Now, the other time I actually, talk about statistical model. And I said statistical model is a family of a probability model. And one of the statistical model is Bernoulli distribution. Okay. Now, Bernoulli distribution, okay, I said is characterized, by two possible outcome. Now, the next on the line of the statistical distribution is what we call discrete uniform distribution. But let me tell you this. We have two types of uniform distribution. We have a discrete, okay? We have continuous, okay? But the one we want to talk about now, the one we want to focus on now is a discrete uniform distribution. Now, what do we mean by that? When we say discrete uniform distribution, take a look at this. This is how many, can somebody tell me for extra credits? How many elements do we have in this sample space, the one I circle now? Can somebody tell me?
There
Oh,
are
and
And
oh my God, a good number of you
Mm.
say and. Good job. Those of you, I want you to be sincere with me now. Those of you who say and, send a message to me for extra credit. Send it to my email. Whether you say and or you chat with me and send a message to my email for extra credit. Be sincere, okay? If you know you mention and. Okay, now take a look at this. The other time I introduced you to some, we're talking about finite probability model. And I said, well, when you talk about finite probability model, it means the sample space has countable numbers of elements. Okay, right now, initially I started with the one element in the sample space. From there, I moved to 2 elements in the sample space. From there, I moved to 3 elements in the sample space. But right now, I'll actually move to n elements in the sample space. Okay, and you know what? We want to use this to explain discrete uniform distribution. Now I have x1 up to xn. What is an example of this? Maybe I actually have a die. Okay, I flip a die. How many sides do we have in a die? 1, 2, 3, 4, 5, 6. There's an example of that because we have so many elements in this sample space. Okay, so this is an example of that. And you know what? If the probability of each of these outcomes is the same, then we're talking about uniform. Look at the word uniform. Okay, when you have a die, okay, you toss a die, okay, you flip it. What is the probability of a 1 showing up? 1/6. The probability of this, of showing up 1/6, of 2 showing up 1/6, of 3 showing up 1/6, of 4 showing up 1/6, of 5 showing up 1/6, of 6 showing up 1/6. It means elements in the sample space has equal chance of occurring. That is, they are equally likely to occur. Okay. Now, if I want to generalize now to n, then I'm going to say the probability is 1/n for I start from 1 to n. Look at that. Even though okay, go ahead.
Can you relate that to the function that you just circled just now, and how that would be able to figure out the actual probability of 1/6 mathematically?
Oh, Okay, so actually, well, what I'm trying to say in essence by discrete or uniform is that if I have a particular number of events, and since they are equally likely to occur, each of them will have equal probability. Then if they are 10 in number, okay, the probability of each of them will be 1 over 10. If they are 6 in number, the probability of them will be 1 over 6. Therefore, if I want to talk about the probability mass function, if I want to generalize for a sample space that have n events, then this is a formula, which is, when I say f of xi equal to 1 over n, what do I mean? I mean f of x1 1 over n, f of x2 1 over n, until I get to the last one 1 over n. Does that make sense to you now?
Yeah, so then just to make sure with this, when it comes down to it, so if you're the sample size of like what you did was 1 through 6.
Exactly.
You just plug in or x1, which is 1, in for n, and then sequentially do that in order. Is this correct? Or I just want to make sure that I get this math right before I, or at least I'm understanding like the math part. I do understand what you did right there.
Okay.
The plugging in for n part.
Oh, are you trying to say this like, okay, when n equal to 1, are you trying to say you're actually going to have 1 over 1? Is that what you mean?
Yeah, that's what I'm trying to say.
Oh, no.
So that is not screw.
Okay, now let me tell you what we're plugging in. Look at this. Do you see this? That is I, right? Now, that very I has to do with the 1 here. If I equal to 1, I mean f of x1. Okay? If I equal to f of x2. Now, I want to award an extra credit for your question. Do you remember we talked about one of the type of function yesterday where f of x1, where if you have different inputs, you're actually going to have the same output? Can you remind me of that type of function? Can you remind me? Because this is going to be 1 over n, all true. When I have different values for x1, x2, x3, I'm still going to have the same output. Do you remember
the name of the function? I know what you're talking about, Professor. Okay,
what is the function? Oh, okay, it is constant function. Do you remember constant function?
Yes.
Exactly. That is what you're going to use here. Yesterday, I walked you through a constant function where you have different inputs, okay? The output is the same. That is what happened here, okay? The I that you see here, we are only changing I to be 1, I to be 2.
All right.
Does that make sense?
Yeah, that makes total sense.
Okay.
Thank you.
You're welcome. Now, this is discrete uniform, okay? That is what we mean. The event actually they're equally likely. So we're still coming to do some properties of this discrete uniform, trying to get the mean, trying to get the variance, but not now. Okay. Now, yeah, I think those are the examples you can read more. Okay, the next thing I want to talk about now is what we call support. What do we mean by support? Okay, if S is a sample space of a probability distribution, every probability distribution must have a sample space. And you know what I mean by sample space? Collection of possibility. And if F is a PMF, okay, then the support of that distribution is this. What do we mean by that? Support is more or less like telling us, we have elements in the sample space. At least we have something in the sample space with the corresponding probability. And what we're trying to say is that the probability has to be greater than 0. Let me tell you this. We know in theory, probability can be equal to 0, but that's an extreme case of probability. Okay, that's an extreme case, because when probability equal to 0, you are talking about that's an uncertainty. That's an extreme uncertainty. Okay, but we live in a world where we are not going to more likely to experience the extreme values of probability. So take a look at that. Okay, but you know what? We have a condition for that. That is f of x equal to 0 except for x in the support. So take a look at that. That's just for divination. I quickly got to move now. You don't necessarily need all that. I think I've explained all this. Now, the next thing I want to talk about is Vena measures. Of course, when you have a sample space, we have an event in a sample space, and we have, if every sample space have a subset, which I've already explained, right, before. And you know what? If F is a PMF, which is a probability mass function, you may want to find the probability of event A. Okay? You may want to find the probability of an event A. And the probability of an event A will be defined as this. It's more or less like you're actually going to sum f of x. And a situation where you have 0, then it means you don't have elements in the sample space. Because the probability, this actually means empty. Okay, when a sample space is empty, the probability associated with an empty event is basically 0. That's what we mean. Okay, so that's exactly what we mean. Okay, therefore, when you take a look at this definition now, okay, a function that we can actually call probability measure, okay, map event to real numbers. Okay, we actually go from event A to the probability. That's what we mean. You have an event, and every event has a corresponding probability. You get what I mean? Okay. Now, if that is the case, I will quickly take you to, example now. Take a look at this example. Okay. Please, I wanted to take, pay attention to this. In the midterm one, okay, you are likely to say something that is related to this. Now, consider a probability model with a PMF, okay, and you have 4 different type of nature. X can be 1, X can be 2, X can be 3, X can be 4. But you know what? This is not uniform. You know why? Why it is not uniform? It is not uniform because every event has different probability. This is the sample space, right? 1, 2, 3, 4. The probability of x1 is 1/10. Some of you may be wondering, how did they actually arrive at that? Because maybe looking at the past antecedents, the frequency, the numbers of time they actually record 1, okay, out of 10 is 1. The numbers of time they record 2 is 2. The numbers of time they record 3 is 3. The numbers of time they record 4 is 4. Okay, so right now, you are given this state of nature with a corresponding probability. And we can ask you a question. And what is the question here? Take a look at this. What is the probability of the event? Now, let me tell you this. The other time, when we're defining events as a subset, I'm going to show you now. Right here, okay, we said a subset of a sample space is called an event. I'm going to give you an example where if I'm using this 1, 2, 3, 4, 5, 6, maybe I'm talking about a die, and I say, okay, what is the event of even numbers? Even, look at that, even numbers. That would be 2, 4, 6, right? I can say, okay, what is the event of odd numbers? Odd numbers, okay? Of course, the odd numbers is actually 1, 3, 5. Look at that. So this guy here and this guy here is a subset of the whole sample space. And you know what? We may want to find the probability associated with event of even numbers. We may want to find the probability associated with the event of odd numbers. You get what I mean? Okay, that's exactly what we want to do here. Now take a look at the in the question now. Okay, you are given this scenario and they want you, what is the probability of events, that event? Oh my God. S greater or equal to 3. I want to find the probability of A, which means I want to find the probability of S greater or equal to 3. When I say S greater or equal to 3, I mean X equal to 3 plus X equal to 4. Look at that. The last one is 4. Greater or equal to 3, it means I'm actually going to start from 3 and I'm going to end up in 4. Now, what is the probability of this? S equal to 3 is right here, which is 3 over 10 plus. What is the probability of S equal to 4? Look at that. 4 over 10. Then when you add up, when you add that up, that will be 7 over 10. Therefore, the probability of A is 7 over 10. Is there anyone who want to ask question or who need clarification about how I figure out the probability of A? Okay, if you want to find the probability of this, look at that. S greater than 3 is just 4 over 10. The probability of S greater than 3, greater than 3, it means it's going to be 4. Can somebody tell me now for extra credit, what is the probability of C?
0.
0.
Okay, good job. Oh my God, those of you that said 0 should send a message to me for extra credit. Good job. Good job. Okay, now these are just what I've mentioned before. The probability of A is like summing. Okay, I think I'll show you that. Okay, I just use an example. I think I've walked you through all these. These are just stories. Okay, now the next on the line is random variable and expectation. Okay, this is also going to be the part of the next material, but let me first prepare our mind. What do we mean by expectation? Expectation is more or less an average. Okay, if I have a probability, for instance, I will quickly, if I want to find, if I give you this, give me 1 second. If I give you this guy here, and I say find expected value of X. Expected value of X is going to be summation X f of X. That is a law. It means I'm going to multiply that 1 by 1 over 10, 2 by 2 over 10, 3 by 3 over 10, 4 by that. So the expectation is average. So it's going to be 1 times 1 over 10, 2 times 2 over 10, 3 times 3 over 10, 4 times 4 over 10. That is what we mean by expectation. Okay? Because we want to know what is the average. Okay, situation where S can be 1, can be 2, can be 3, can be 4, and they have different probability. Okay, how can we actually determine the average? This is what we call a weighted average. We call this a weighted average. Okay, so take a look at that. That is exactly what we mean. Okay, and that is part of what we're going to do in the next lecture, because so that is part of what we actually going to do. Okay, now that is what we mean by the expected value of X. So the expected value of X is just an expectation operator for the parameter value. Okay, I'll just show you now. Okay, the next thing is basically Cartesian product. Okay, and what do I mean by that is just if I, for instance, if I have, if A is 1, 2, and B as maybe 2 or maybe 3, 4, I'm just assuming, or maybe B is 3, 4. Okay, what is the Cartesian product of that? Okay, it's just going to be 1, 3. Okay, 1, 4. Okay, 2, 3. Okay, and 2, 4. Okay, so that is what we mean by that. It's like taking one to multiply the other, and situation where they are the same, then you're actually going to have a squared. That's what we are trying to define there. And we can have a situation where we have 3 of that, and when they are equal, you're actually going to have that. And your X is going to be taken from A, Y taken from B, and X taken from C. Okay, so those are kind of easy. And this is the generalization, of that. Okay, so you can actually read that up. Okay, and you can try this. I'm giving you this as an exercise. Okay, I think I walk you with this expected value of S, just distance, this, that, and that. But if you want to do this, okay, you can try this. Okay, X minus 3. Okay, you first plug in. Let me give you a clue. okay, x minus 3 all squared. The formula is going to be summation, okay, s minus 3 all squared f of x, okay? You know, don't forget, and your s can be 1, 2, or 3, or 4. So if you try that, and you can send it to my email for extra credits, for those of you who will try to, you know, work that out. Okay, so that is going to be the end of my lecture today, because what I'm seeing here is part of what is also in the next lecture. So is there anyone who need clarification before I go today?
I have a question
Go ahead.
about
Go
when
ahead.
we think about events and measures. If the random variable x is continuous, would the formula for the probability measure use integration instead of summation, or can you not
Exactly.
use?
Exactly. Okay. If it is continuous, we're going to use integration. But if it is discrete, we're basically going to use summation. You know, we're still going to come across a situation where we're going to apply integration by the time we're dealing with a continuous random variable. You are right.
Okay, gotcha. Thank you.
You're welcome. Okay, if you really enjoy my statistical party today, I need you to say yes, or you comment yes. Okay, thank you so much. Okay, I'm actually going to have my office hour. You know, today is Wednesday. Okay, in case you need a question to ask me. Okay, I want to appreciate everyone. I really appreciate everyone who attended my lecture today. I hope you're enjoying it. Until tomorrow, then I'm actually going to come your way again. Make sure you stay safe and have a very beautiful day. Bye for now, everyone.
Thank you.
You're welcome.
Thank you for another amazing lecture, Professor.
Thank you.
You're welcome. Thank you too. Thank you, everyone. Yeah.